Hello everyone, welcome to the 23rd episode of this series. In this video, we'll learn how to prove and disprove subspaces. So in the last episode, we learned about subspaces and these are just non-empty subsets in Rn that are closed under addition and scalar multiplication. And some of the examples were the solution set to homogeneous system of linear equations, and then kernels, eigenspaces, and images to a matrix. Okay, so the first thing we're going to learn is how to show that a given subset of Rn is not a subspace. So all we need to do is find one specific counterexample to one of the properties. So let's look at an exercise. So we're given a set S, and this set S is a collection of vectors that form the unit circle in the plane. So this is the collection of all vectors with entries x and y, where x square plus y square is 1. And we have to show that this S is not a subspace of R2. So to show that, we'll just pick any vector we want in S, and I'm going to choose 1, 0. And I'm going to multiply it by any scalar other than 1. So I multiply it by scalar 2. So that tells us that 2 times the vector 1, 0 is not in S, because when you take the sum of the square of the entries, it ends up being 4, which is not the same as 1, which was the defining condition of this set. So that tells us that S is not closed under scalar multiplication, and for that reason, it cannot be a subspace of R2. On the other hand, showing that a given subset S of Rn is a subspace is a little harder, because we need to show that S is non-empty and that the two subspace properties always hold. So we want to show closure under vector addition and scalar multiplication. And we have to do this for every possible case. So we can't just take specific examples and verify them. We must work with general cases, or we must work a little bit more abstractly. So let's talk about working abstractly. And we've done this in class a little bit at this point. We've worked on some proofs. So we work with arbitrary objects like numbers, vectors, sets, but sometimes with specific properties, or sometimes as generic as possible. And typically we avoid examples. So instead of working with a particular number 5, we might work with a particular number R, or like in a different scenario, a solution X to a given equation. And this working abstractly has a few advantages, because we might see that there is an argument that works in many different situations, so we can just generalize it. And if you're trying to show a particular property that holds for infinitely many cases, we can't do it by hand. We can't check infinitely many examples, so we can just try to give a general argument. And these general arguments are essentially what we call proofs. So let's look at like a sketch of a proof, at least for showing that something is a subspace. So we're always going to start by communicating what we are assuming. Let V and W be in my subset W. Then you're going to explain what you're doing so that the reader understands what is actually happening. And once you're done, once you achieve your goal, you're going to conclude the argument by restating what you have shown. So one of the things that I learned in my time as a student was that when you're trying to present something, especially a proof, you start by saying what you're going to do, and then you do it, and then you say what you just did. And that's a very effective communication. Okay, so let's look at another exercise now. We're given a subset of R3 called W, and this is the collection of all vectors whose entries are the same. And we have to show that W is a subspace of R3. So let V and W be in the subset W. This means we can write them as vectors A and B for some numbers A and B in R. Why? Because every vector in capital W is a vector whose entries are all the same. So, for some numbers A and B, V is going to have A, and W is going to have entries B. And when we add them, we get um, A plus B, A plus B, A plus B. And again, this vector has all the entries equal to each other. And that means that V plus W is in the set W, and therefore W is closed under vector addition. Now, in a similar fashion, we're going to prove scalar multiplication, or rather closure under scalar multiplication. So we're going to start with the vector in W and a scalar C in R. That tells us that this V is equal to A for some A in R. We multiply the scalar C to this vector V, and we just get a vector with entries CA. And again, all the entries are the same. So C times V is also in W, and therefore W has to be closed under scalar multiplication. And because the two properties hold, and because it's non-empty, because 0 is the simplest example of a vector that has all the entries same, we conclude that W is a subspace of R3. Okay, so let's look at another exercise before we end this episode. In this problem, we have to show that the kernel of any m by n matrix A is a subspace of Rn, and we have to prove this directly from the definition of subspace. Note that this property appeared as a theorem in episode 22. So since A times the zero vector is the zero vector, we get that the zero vector is in the kernel of A. So that gives us that the kernel of A is non-empty. Now, for closure under addition, we start with two vectors V and W in the kernel of A. Then that gives us that AV and AW have to be 0 by the definition of V and W being in the kernel. And because matrix multiplication distributes over addition, we get that A of V plus W is just AV plus AW, and that is just, again, 0. So V plus W is also in the kernel, and therefore the kernel of A is closed under addition. Next, let C be in R, and let V be a vector in the kernel of A. Then, just by definition, AV is 0, and therefore A times CV, which is just C times AV, ends up being 0 as well, which means that CV is also in the kernel of A, and therefore kernel of A is closed under scalar multiplication. And we conclude that kernel of A for any given matrix A is a subspace of Rn. And with this, I would like to end this episode. Hopefully things were clear. I will see you guys soon. Up until then, happy learning.